In this presentation, I'm going to be talking about SALT time-resolved optical observations of the low-mass X-ray binary system and black hole candidate system, Swift 1357.2-0933. So this is part of a wider transient follow-up program being conducted at SALT, which began in 2016. And it involves the observations of transients across all different object classes. And it's a large program involving 5 South African institutions, 4 other SALT partners, and a total of 36 co-investigators, including graduate students. It allows for the fact that we can respond rapidly to target of opportunity alerts. We can monitor objects on different cadences depending on the type of system. And furthermore, the data becomes available very rapidly, typically within 12 hours of the observations being taken. So it covers a whole wide range of the phase space of transient systems, which is shown in this diagram on the right, produced by Jeff Cookie, that shows different timescales and luminosities of many different types of transient systems. And so the objects that are of interest to the collaboration are listed here. I'm not going to go through any details, but the last one highlighted in red is, of course, X-ray transients, which is the subject of this particular presentation. So these include transients that are classified as high mass X-ray binary systems. So these are mostly neutron star accretors, typically from B companion stars, and typically with quite long orbital periods. Then there's the low mass X-ray binaries, of which the transient systems are typically 3/4 of them are black hole accretors. And these go through, obviously, outburst phases, state changes as the accretion rate changes. So the little diagram on the left shows the sort of idea, a cartoon idea of what the system might look like, showing all the various contributors to the emission in the system in the outburst state. And you can see there that the predominant bright area is the accretion disk surrounding the compact object, black hole or neutron star. In the quiescent state, however, the accretion disk becomes very faint because the mass transfer is diminished significantly. And you see mostly emission from the secondary star and perhaps a little bit of emission from the outer part of the accretion disk. So these are typically X-ray bright systems when they go into outburst. They're relatively rare outbursts, perhaps decades apart for many. And they also involve optical brightnesses, changes in optical brightness by anything up to 8 magnitudes or so. And then there's a whole host of phenomenology related to the accretion, the inner part of the disk, the production of relativistic jets, which is often termed, these systems are termed microquasars, which of course can be detected in the radio, and a lot of work has been done in that area. It's challenging to determine system parameters in these because when they're X-ray active, the accretion disk is the dominant source of the luminosity, and you only really are able to study the secondary star where you might get, for example, radial velocities from the motion of the photospheric lines in the quiescent state, which is typically when they're very faint and therefore quite hard to detect unless you have large telescopes to do this. So Swift J1357.2-0933, which I'll just call Swift 1357 from now on, is a black hole X-ray binary. It was first discovered following a Swift back observation in 2011. It's a high galactic latitude source, and at the time of discovery was thought to have a luminosity of around 10 to the 35 ergs per second. The interesting thing about this, though, was in the original observations of the first outburst, that the optical light curves, which are shown at the right here, showed frequent dips occurring on timescales of a few hundred seconds or so. These dips were seen to repeat in frequency with a decreasing frequency or longer period between the dips as the outburst progressed. And on the left here, you can see the actual intensity of the system in X-rays and optical during that first outburst. And this was reported, these dips were reported by Coral Santana et al. In 2013. So those observations led to a mass estimate of about above 9.3 solar masses for the unseen black hole companion. But interestingly, the system has also undergone other outbursts. And so the observations that I'm reporting here were for the outbursts in 2017 and 2019, the latest two. And the observations consist of both photometry with SALT using what's called slot mode photometry that gives 0.15 second time resolution, and frame transverse spectroscopic observations, typically with 30-second exposures and no dead times in any of these data. Interestingly, there was no correlation between the optical and X-ray fluxes. There were actually overlapping observations between X-rays and optical, and showed no real correlation. And this plot here shows the SALT high-speed photometry showing the dips that had previously been seen. And as you progress through the outburst, you see that the time scale between the dips increases significantly. So a model has been developed for this system, and the observations that I've just shown you here have been published in a paper by John Paice and collaborators, which involves the multi-wavelength observations with the X-rays and optical involving both SALT and ultracam observations. And the dips have been postulated to be due to vertically extended parts of the accretion disk in the inner region, which periodically, due to the Keplerian rotation, occult the inner source of luminosity, causing a dip at the Keplerian frequency. And during the outburst, these extended regions propagate outwards in the disk, so the Keplerian velocity, sorry, the Keplerian period increases, and so the dip frequency decreases. So these plots just show how the dip frequency evolves. The observations that were conducted in the original outburst and published by Coral Santana are shown in the black crosses. In comparison, the blue and red show the recent 2017 outburst, with the blue dots being the SALT observations and the red being ultracam with the NTT. On the right shows the vertical lines numbered show where these observations occurred during the X-ray decline. And so the behavior is quite similar between the two times of outburst, although there is an offset between the 2011 and 2017 outbursts. And the dip period increases from 100 to about 500 seconds over about 80 days. Interestingly, we also undertook outburst spectroscopy, which overlapped one of those dates of the photometry. And what we discovered was periodic absorption in the spectra on the same time scale as the photometric dips. And so you can see in this trailed spectrum, where the data were taken about every 100 seconds in this case, you see these dips, particularly in H-alpha, but also prevalent in the other Balmer lines, and interestingly in helium-2. And what you can also see is that they're somewhat blue shifted from the rest velocity. So this is actually a plot showing the stacked spectra during a dip. And you can see the nature of the absorption for the Balmer, and on the left, the helium-2 line, where the vertical line shows the rest velocity. So they're systematically blue shifted, as you can see. Helium-2 in absorption has never been seen before in a low mass X-ray binary, which was an intriguing result that we followed up on. So in fact, we have used the fact that this blue shifted absorption is in a sense a smoking gun for the indication of outflowing material. And one of our co-authors, Jamie Matthews, used a code to model the absorption in a disk wind and discovered that you can actually mimic the absorption, optically thick absorption, by requiring a high X-ray luminosity, much higher than previously thought. These were published in 2019 by Charles et al., showing these data and the models. Subsequent to this, observations were taken in the latest outburst in 2019, and it shows the same dips, but intriguingly now with somewhat high resolution of 30 seconds, one can see that the lines are tilted. And this indicates that the motion is changing from a blue to a more blue shifted to red shifted over the period in which these observations, or over the dip period. And this is another observation on the 1st of June showing the same tilt. So we are sort of explaining this as a possibility of the fact that during the dip period, the obscuration of the receding matter is being systematically more absorbed, which starts off being more blue shifted and then gradually increasing in velocity, or possibly a deceleration effect. So in summary, Swift 1357 shows some remarkable and unique outburst behavior. This variable quasi-periodic dipping is the first time that's been observed in such a system. The helium-2 in absorption is also a unique aspect, and the moving absorption lines during the dips, the line tilts that indicate a blue to red shift, is also quite intriguing. Many questions remain about this system, although an initial distance estimate of 1.5 kiloparsecs was postulated from our models, and the fact that we need a very high X-ray luminosity to explain the disk wind, but therefore has to be more absorbed given what we actually detect. This implies that the system is over 6 kiloparsecs away. And being at high galactic latitude of 50 degrees means, of course, it's way out in the halo, or much further out from what was previously thought. It is a very high inclination system, which is the explanation for why we don't see more X-rays and why these dips actually occur. And that may be the actual key point of what's causing this, a very special viewing geometry where we see the accretion disk corona from the region that's unobscured. But the X-ray system is consistent, although a question remains, is the X-ray spectrum consistent with the low hard state? What's driving the inner disk vertical extents and the spiral arms or warps that progress out? And why is this the only source that we've come across doing this sort of thing? So that's the end of my talk, and thanks.